Hi guys, welcome back to Physics Form 4 KSSM. So today we are going to discuss Chapter 3, Gravitation. So I think this topic is very interesting. We are going to discuss about gravity, we discuss about satellite and all about universe. Okay, let's get started. Okay, Gravitation, Chapter 3, you can refer to your textbook on page 76. Okay, for the first part 3.1, we are going to discuss about Newton's Law of Universal Gravitation. So you must be able to explain the Newton's Law of Universal Gravitation. So you can look at the diagram. This is a satellite. So you can see here, there are a lot of satellites that orbiting surrounding the Earth and the Sun. So can you imagine how can the satellite can stay there orbiting without falling to the ground? Okay, so in this topic we will discuss about what caused the satellite able to orbit around the Earth without fall back to the ground. So something related to gravitational force. Before that, we'll look at this video. This is an animation about the launching of rocket. So I hope you still remember the principle involved for this launching of rocket, that is a principle of conservation of momentum. So the hot gases release out, produce momentum downwards. At the same time, it will produce upwards momentum that causes the rocket to move upwards. So you can see now the rocket starts to release some part of its body in order to reduce its mass so that it will gain high velocity. So when reach the outer space, so you can see still remove its parts. So that part will be removed, there will become space debris, which is not function. The parts will also orbiting or floating there together with the satellite. So this is how they send the satellite to the moon or to the outer space, so that it can be used for so many purposes like telecommunication, for the climate detector and all that. Okay, that's all. Okay, so how can the satellite able to orbit surrounding the moon or surrounding the Earth, or the moon surrounding the Earth? So according to Isaac Newton, there is a universal force that caused this situation. So the idea coming from an apple that fall down to the ground. So Isaac Newton realized that the motion of a falling apple and the motion of the moon were both actually the same motion caused by the same force, the gravitational force. If you look at these two situations, so there are force between two objects, as the example for the apple case, the apple and the Earth, or the moon and the Earth. Okay. Okay, now comes the idea about universal gravitation. So Newton's idea was that gravity was a universal force acting between any two objects. It's not just discussed about apple and the Earth, that apple that fall down towards the ground. But you also will discuss about planets between moon and Earth, between planets and Earth, and satellite and Earth. So meaning any two objects. Okay, at Earth's surface, we have discussed in Chapter 2, 2.8, we have discussed about the concept of weight. Newton knew that the gravitational force on the apple equals the apple's weight mg, where g equals 9.81 meters second to the power -2. So you can see an apple that fall down is due to gravity pull, so its weight w equals to mg, always directed downwards. So Newton produced Newton's Law of Universal Gravitation, which conclude that gravitational force is directly proportional to the product of masses of both objects. And then another statement, gravitational force is also inversely proportional to the square of distance between the centers of the two objects. So we have here we have two bodies here, body 1 and body 2. Body 1 mass m1, body 2 mass m2. The separation distance between two centers, center to center, we mark as small r. Okay, so from the statement produced by the Newton, we can write the relationship. So the first one, F is directly proportional to product of masses of two objects. Thus we get m1 times m2. And then for F, the second relationship, F is inversely proportional to the square distance between the centers of the object. So meaning F directly proportional to reciprocal of square distance r, or r squared. So by combining these two relationships, thus we get F is directly proportional to m1 times m2 divided by r squared. Okay, so this is what stated by Newton's. So we call it universal law of gravitation. So the gravitational force acts between any two objects can be stated in this form. There is Fg directly proportional to m1 m2 divided by r squared. Okay, so that one we call it law of universal gravitation, or Newton's law of universal gravitation. So we have the relationship. Now we want to produce formula. From the relationship we put equal sign, then we must put the constant. So the constant here is G, capital G. So the value of G is determined from experiment, and this value is also known as universal gravitational constant. The value is 6.67 times 10 to the power negative 11 Newton meter squared per kilogram squared. Okay, now let's look at some example using the formula. Look at example 1. Calculate the gravitational force between a durian and the earth. Mass of durian 2 kg. Mass of the earth 5.97 times 10 to the power 24 kg. Distance between center of durian and center of the earth also given. So now we use the formula. F equals to G m1 m2 divided by r squared. So just substitute all the values. So you must be able to use your calculator to calculate, because involving a larger and smaller area here. So you solve it, you get 19.63 Newton. So meaning the gravitational force between durian and earth is 19.63 Newton. Or we can say the durian is pulling the earth with force 19.63 Newton. At the same time, the earth is pulling durian at 19.63 Newton also. So opposite direction, same magnitude. So for the durian, with this force, the durian will accelerate towards the earth. But with this force, it does not give any effect to the earth. Looks like earth will not moving. That's why we can say, in this case, only the durian that accelerated towards the earth. You can use the formula F equals to ma to show the acceleration of the earth with this value of force, because we have mass of earth here. Example 2, a rocket at a launching pad experiences a gravitational force of 4.98 times 10 to the power 5 Newton. What is the mass of the rocket? Okay, all the information given. So we use the formula F equals to G m1 m2 divided by r squared. Let's assume mass of rocket is m2. So we just substitute all the value. The value of F is given. Then we want to find m2. So you just make it m2 as a title of this formula. So you solve the problem, you get 5.07 times 10 power 4 kilograms. So this is the mass of the rocket. So this is one type of problem solving by using the Newton's gravitational law. Okay, now let's look at from the formula also, we can explain the factors that affect gravitational force F. So of course, from the formula, the first factor will be the product of masses of the two objects, meaning the masses of the two bodies or object. The second one is the distance from the centers of two bodies. From the relationship, we can say the larger the mass of the two bodies, the larger the gravitational force, or vice versa. And then gravitational force decreases when the distance between two bodies increases, meaning the gravitational force decreases when an object is far from Earth, for example. Okay, now we want to relate between gravitational acceleration small g. I think you know already this one, we have discussed in chapter 2. On the surface of the Earth and universal gravitation constant, capital G. Okay, gravitational force causes object to fall with acceleration g. So this small g is acceleration due to gravity. So for falling object, especially free fall object, it will experience this acceleration g. So from the Newton's second law of motion, we have F equals to ma. Thus we get gravitational force is equivalent to mg, that is weight of the object. Okay, now if we consider the gravitational pull between the object and the Earth, so this one is stated by Newton's universal law of gravitation. So we use the formula G m, capital M, small m, divided by r squared. The capital M actually is the mass of the Earth, and the small m is mass of the object, because we consider object and Earth here. Okay, so now these two gravitational force are equal, then mg equals to g m divided by r squared. So the small m can be cancelled. So in the end we get gravitational acceleration equivalent to capital G, gravitational constant, multiply mass of Earth divided by distance between centers of two bodies squared. Okay, so we have the formula for you to calculate gravitational acceleration. Okay, the factors that influence the value of gravitational acceleration. So we just refer to the formula. As you can see, gravitational acceleration equivalent to gravitational constant multiply mass of the Earth divided by distance between center of Earth and center of the object r. From here, we can see the value of capital G is a gravitational constant, of course constant, and mass of Earth also is constant, meaning these factors are constant. These two factors are constant. So from here, the value of G actually depends on only small r. So we can say the more the distance, the less the gravitational acceleration. So all we can say here, G is inversely proportional to the square of distance between centers of two objects. Okay, now we discuss more about the value of G. Okay, now we have a graph of G against R that shows value of G with various value of G and R. Okay, now we assume this is for Earth. At the center of the Earth, G equals to 0 Newton per kilogram. So you can still remember this is the unit for gravitational field strength. So meaning the value of G at here equals to 0 at the center of the Earth. So when from the center of the Earth towards the surface of the Earth, you can see the graph shows the value G directly proportional to distance from center of the Earth. You can see the value of G increases until the value is equals to G, small g equals Gm divided by r squared. The capital R represent radius of the Earth, meaning at the surface of the Earth, the value of G will become 9.81 meters second negative 2. Okay, what happened for the object which is further from the Earth, like distance double r or triple r? So in this case, you can see the graph shows the value of G decreases. So it decreases. So why is this happen? So you go back to the same formula. So G, small g, gravitational acceleration equivalent to G times m divided by r squared. So when r increases, the value of G decreases. That's why you can see the value of G becomes smaller than 9.81 meters second negative 2. So it becomes smaller and smaller when the distance r increases further. So you can see the statement here, value of g inversely proportional to the square of distance from the center of the earth. Okay, now we want to determine the value of g. We have an example here. We have a satellite at height h from the surface of the earth. So define here, height of the satellite from the surface of earth is h. Capital R, radius of earth. Small r, distance of satellite from the center of earth or radius of the orbit. Okay, now we want to determine gravitational acceleration for the satellite. Okay, so we use the formula G equals, should be m here. I left out one m here. So Gm, capital M, divided by r plus h squared. Why need to plus h here? So r is from center of the earth to the satellite. So from center, we need to plus radius of the earth plus height h. So that's why the value is r, capital R plus h here. On the surface, if object on the surface, so h equals to 0, then distance from center of the earth r equivalent to radius of the earth, capital R. So meaning we have the gravitational acceleration on the surface of the earth equivalent to g, gravitational constant, multiply mass of the earth, divide by radius of the earth. Meaning we can calculate what is gravitational acceleration on the surface of the earth if we have all the information here. All these are constant. Okay, so meaning the value of g on the surface of earth is constant. Okay, look at example. Mass of earth is given, radius of earth is also given. Calculate gravitational acceleration on the surface of the earth. So g also given. So we use this formula. Okay, gravitational acceleration, gm divided by r squared. Now the word surface of the earth meaning distance between centers of the object equivalent to radius of the earth. And then we substitute, we get 9.81 meters second negative 2. So this is the value that we use when we solve problems involving object at the surface of the earth. Okay, now example 3. A radar imaging a satellite orbits around the earth at height 480 kilometers. So what is the value of gravitational acceleration at position of the satellite? Now height given 480 kilometers. You need to convert to meter because we use SI unit in our calculation. So you substitute all the values, G, M, and then the value of small r, distance from center of the earth to the satellite. So you just add radius of the earth plus h. So you add here. So you get finally g equivalent to 8.49 meters second negative 2. So this one shows that the value of g decreases when the object is further from the center of the earth. Okay, why we need to know the value of gravitational acceleration? So it's very important, especially for the astronaut. They are going to the moon or to outer space. So therefore, the formula that used in order to know the value of g is still the same formula, gm divided by r squared for any distance between two objects. So we can use it to calculate gravitational acceleration on the surface of other bodies such as planets, moon, and sun. So knowledge is very important for space exploration and continuity of life. So you can do more research on this, search in the internet, okay, about this topic. Okay, does the gravity give effect to human growth or not? So we are going to discuss about effect of high gravity and effect of low gravity. Okay, the first one is high gravity, so you can read through. Difference in density, density increase about the bone density and all that, or the liquid density inside our body. Bone fragility seldom happens. Size of lung compressed becomes smaller. Blood circulatory system, heart pumps harder. Blood pressure, high muscular system becomes stronger. Low gravity, especially astronaut going to the moon. This is what the effect that might happen. Immune system is weaker, skin becomes thinner, vision deteriorates. Okay, height increases almost 2 inches. Anxiety, face swelling, and legs become smaller. Space sickness, seasickness, car sickness, and bones become less tense. They quite suffer if you look at the effect of low gravity, so meaning astronaut will suffer a lot. Okay, so you must grateful that they are willing to go there to study about space. Okay, so this is all about topic 3.1. The first part of 3.1. I will continue in the second part for the next video. So I hope you can subscribe, like and tap for more oncoming videos. So do support physics teacher. Thank you.